Hello, can you guys hear me? Yes. Type me some chat, say if you can hear me.
Yes, we can hear you.
Excellent. Thank you very much. We can start. So I'm going to share my screen. Okay, good afternoon. So this is our last week of lecture. So what I'm planning to do is for Friday's lecture is a week 16b. We totally do this one for review. Okay, for review. So today we are going to pack everything into this lecture. To do first is for internal model principle. Okay. Then we are going to talk about disturbance observer. Okay. Observer. Okay. Then we are going to talk about Smith predictor. So when you have a delay, how to handle the delays. Okay. Then we are going to have a very brief overview of what is LABView, because many of you, when you get to the industry setting, people will ask, oh, have you learned LABView in a class setting? Yes, you can tell them, although maybe less than 10 minutes. And programmable logic, for this the sequential control. Sequential control. You do this first, then you do that kind of sequence. How that was done using a programmable logic controller called programmable logic controller, PLC. Okay, PLC. So these abbreviations are also valid for final exam. Okay. Okay. So I have 16 people, 15. It's okay. I'm recording it. Okay, I'm recording it. So you can see we have a very busy agenda today. Okay, busy agenda today. Let me show you our last week's. It's called Advanced Controls in Mechatronics. All those. Perhaps I'll spend time about a PID tuner. That's actually we mentioned it. So it's called PID tuner. Well, auto tuner, automatic tuner. How to do that? So because in the industry setting, you are buying a PID controller box, then this must be an automatic tuning feature built in. So what I'm going to do the first is IMP. So the story starts by consider a motor, velocity servo. So velocity servo system, meaning you have a simplified. You add a voltage, then you are going to have a speed, right? So you also could have integration. You can theta is a precision. Okay? So you can see that we have a S in here. If we do a speed servo here, so I have theta desired. I want you to turn like 90 degrees. It will turn 90 degrees. So we have learned that if I put the controllers here as a KP, then what is this arrow signal? This arrow signal is when t goes to infinity, we call t goes to infinity, we call this the ESS, called steady state arrow. Of course, I want this one to be 0, but how we can ensure that it's is 0? We have learned something called system type. System type. So in this system, so all the loop in here, how how many integrators in there? So it's called s to the power of 1. Okay, in the denominator, you have a a of s in here, you have b of s in here, transfer function. So you can pull out the s here. So this number is called type. So you know this is a type 1 system, right? So this is type 1 system. For type 1 system, you have learned that type 1 system will give you steady state error, no problem. Even if you only put here, okay? Only a gain, okay? So it's a proportional gain controller, okay? Proportional controller. It's called P controller. But if I have theta t is not constant, but it's a ramp function, then you know that this EFS is not 0 for ramp function, okay? It's not for ramp function. So what you should do, you know that the ramp function Laplace transform pair is S squared. So we have learned that the system has to be a type 2, so that the steady state is error. How to achieve type 2? You need to add Kp plus Ki divided by S. So therefore, in here, you are going to have 2 in here, okay? That 2 will give you the type 2. Therefore, this is 0, okay? So then the controller C of S is Kp plus Ki 1 of S. So this 1 of S will contribute to another 1 of S. Then we together will get this S squared in here. S squared in here. So therefore, we have type 2. So this is type 2. So, but what is IMP? IMP. Internal model principle. Internal model principle. Okay. What does this one say? Let me give you first example. Okay. Let's say example. Let's say that my theta d is actually giving us a sine t. Okay. I want you to track the sine t yet. You want SS is 0. Okay. So in this case, Kp is not going to work. The Kp plus Ki is also not going to work. So what is the correct CFS structure in this case to guarantee this is the case? This one we have to, so no matter how you tune the Kp or Ki, no matter how smart you are, your structure is not right, this steady state error is always non-zero, okay? Cannot achieve 0 steady state. So how to achieve that? Here is the principle says. Principle says if you have a reference, okay, let's say it's a theta desired. If it's Laplace, of course it's a t, okay? It's not necessarily constant. So the Laplace transform of this one, let's say the theta d of s. We should write this one like numerator polynomial of reference divided by denominator of this reference. Can we? Yes. Say for example, in the theta d is 1, then nr is 1, then dr is s, right? dr is s. If theta d is t, then nr is 1, and dr is s squared, right? Make sense? Good. So what is dr for sine? So in this case, nr is 1. Excuse me. Oh, I'm sorry. Then what is the ND denominator? What is the DR? Okay, DR is S squared plus 1, right? Plus 1. So IMP says in a controller structure, this is not right. In a controller structure, okay, you can also write a numerator, denominator, right? And sorry, it should be numerator C is the denominator of C of S, right? This one says that if we want to make ESS at 0, giving set of D of T, okay, given. Okay, so the DC part must be able to factor out the reference, factor out with this reference has to be here. So it's called D reference S has to be here. And you plus another DC bar, whatever you put it here. This one has to be there so that the steady state error is 0. Okay. Okay. So let me give you this. So this is nothing is kind of like system type generalized generalization of this IMP. Okay. Okay. So in other words, so you can say for sinusoid, your CFS must, okay, have 1 plus S squared in here. Then you can say, oh, I have other terms like KP plus KI. Then you can start to tune this, okay? So this total controller follows the IMP principle that the controller structure, this is my controller structure, I have denominator must contain the denominator of my reference. So this is the denominator of reference. So that explains, okay? That explains. So if you have a step, you must have an integrator, okay? So that's the very beautiful of internal model principle, okay? So this is called control structural issue. So this one determines the controller structure. Once you decide the structure, then you can decide the control parameter. So I hope you understand in the controller design, you have to follow first structure of the controller. Second is the parameters. So the PID, this is just one of the many structures. However, depending on the reference, your structure must contain something of the disturbance, it's a reference or disturbance denominator, okay, denominator. So I hope this internal model principle is clear to everybody that is the generalization of the concept of system types, okay, system types. And in general, in controller design, you have 2 work to do. One is controller structure, one is the controller parameters to decide. So how to decide this? Okay, you have to use internal model principle. Okay, because 0 steady state error is the basic thing we want. Okay, it's the thing we want. So that explains internal model principle. Okay, sometimes. So this is very important in your practice. Sometimes, if this is a sin T, you still use KP, then this one is not. It looks like getting smaller. Okay, getting smaller. But if we zoom in, you still see the sinusoid still there. You can suppress the magnitude by increase the KP. Okay, you can suppress it, but you cannot remove it. It's always there. Okay, it's always there. So remember, if we make the KP too big, the system is going to be unstable. Okay. Don't worry if you can kind of capture what I'm writing here. I'm going to export this one and generate a PDF for you, okay? So for this IMP, it's called internal mode principle. So the reason I want to add these things for you today is you will never be a good mechatronics engineer if you do not know this principle, okay? Okay, so this is very essential. However, we don't have enough time to cover all of them. But these are the essential things you should know, okay? So the second one I'm going to talk is DOB, Disturbance Observer, okay? Why this is an important topic? Yes, you do. Because let's use this motor as an example. So you have a GOS, okay? This is your motor, okay? So you have output. Before your motor, you have disturbance D in here, okay? Disturbance D in here. Then you have controller C in here, okay? You have a reference, you have a reference, this is a reference, this is negative feedback, okay? Negative feedback. So how I can reject this guy, okay? How I can reject this guy. Of course, if you can measure this one and you can do disturbance feed forward, okay, to cancel it. So this is all pass, okay. But if you don't, you have a computer control. What you should do? What you should do? What you should do is to pull out the signal here. This is a signal, you know it, okay. This is a U signal is available to you. This is also a signal available to you, okay. This is Y, okay. I'm hoping that going through a box, okay, going through a box, such that the output of the box is an estimation of my D, okay? It's estimation of my D, such that I pull out the D in here and minus this one will cancel it. So this is called observer, okay? Observer, okay? But this sounds like interesting because you simply all these are the software inside the computer control. All these are the software algorithms. Okay, software algorithms. We didn't invest hardware costs, and we still can cancel this guy without buying a sensor to measure it. Sometimes you cannot measure it, right? So what is inside the box? Okay, what's inside the box? So traditionally, people actually want to write this way. This is D, this is G, this is Y. So this is my E. This is summation. This is reference. This is minus. So I pull out here. Okay. So the basic idea is like this. So what I'm doing here is pull out this signal. Okay. And I let this one go to G, inverse. Okay. Go to the inverse. And then I pull out this signal. It's available to me. Okay. And I want these two guys. So because this is already, let's say this is a V, okay? This is a V. So after you inverse, this is also V, okay? Also V. So then this is a V, this is a V equals U plus D. So this is also the V minus this U, okay? Minus this U is plus. What I'm going to get is some signal, which is exactly D, okay? Exactly D. So I pull out the signal in here, okay? And minus. Then by doing that, this is as if there's no D. D is not influencing my system. This sounds too good to be true, right? Okay. This is indeed not possible. Okay. This is just the idea. So let's just use some simple examples. Say, for example, this is K TS plus 1, this is the system, right? Then this is a velocity servo. Velocity. Now this is the motor, okay? Velocity. So we have some disturbance on the motor. For example, what we say, you have elevator, okay? You have elevator. You have different people within the elevator, then it's like the D is different, right? The node is like disturbance. Okay, so that can be treated. So I want this, the elevator's performance is not going to be affected by this load changes, uncertain changes, different number of people in the elevator, right? So in this case, you can do this kind of disturbance observer control. This is the idea, DOB, disturbance observer. So why we say this is idea? Because I'm going to have a Y in here. So if I say this is a velocity server, what's this? This guy will give me what? It's 1 over K. Here I have TS plus 1. Okay? Okay. So which is okay. Well, you have 1 here. Why? But why you need to do this one? This S is DDT, okay? DDT is the idea differentiation of the signal. What if you have some noise in here? This noise will get very amplified, okay? Very much amplified. So this is not what's called physically realizable, okay? Physically realizable. Okay? So whenever you have A of S, B of S, the relative degree is the degree of this one minus degree of this one. So our case here, this relative degree here is 1. But what is the relative degree here? It's less than, it's 0 minus 1, so it's negative 1, okay? So that is not feasible in practice. So usually we talk about the relative degree is greater than or equals to 1. Equal to 0, actually. It could be 0. Say, for example, you have AS plus 1, BS plus 1. So this is relative degree is 0. But if you have a squaring here, that is questionable, okay? That is not considered as physically realizable. So this type of transfer function is not supposed to exist in reality. The same is true here. This guy is dangerous because they will bring me a lot of, this S will give us a lot of trouble, okay? Okay, so what we should do is to, I have this one, right? I have this one. I don't like it, so it's dangerous because of this S. What I should do is I cascade this one, multiply by a Q of S. The Q of S, in this case, it is giving us tau F, okay? S plus 1 is a low pass filter. And I can put a bracket like 1 or 2 or whatever, I put N in here. But in this case, N is 1 will work, right? Because this is, without this, so this is AS plus 1, BS plus 1. This is a lead lag compensator function. So this is okay, we can implement. So when N is 1 is okay, N is 2 is also okay, right? Okay. So then if I put Q in here, okay, everything will be, put Q in here, this will be realizable, right? But if you put Q in here, you also need have a Q in here. The reason is otherwise the D will be, so now it's like your D is not a real D. Your D is a D hat, okay? So the D hat is actually is ideal D times Q, okay? Times Q. If the Q has certain bandwidth, then this is approximated okay. Okay. So this is called so this is called versus realizable DOB. So I'm drawing, this is a realizable DOB. So this has a Q filter. This Q filter. Though Q is 1, then everything is ideal. But when Q is 1, this is not going to be realizable. So that's you cannot do that. So basically, the Q should choose something like that. Okay. So you may wonder why this is good. Okay, why this is good. Let me draw you a body plot. Okay. So in original system, so your T of S. Okay, T of S. Or let's check S of S. So 1 minus T of S is S of S. Okay. Then you do a 20 log 10. Log 10. This, what you are going to get is something like that. So this is your log 10 omega. So this is your 0 dB. Okay, 0 dB. So without using this type of disturbance observer, without using it, so then let's assume that this is our it's something like this. Okay, something like this. So this is my body plot. Okay, it's for sensitivity body plot. But if I add disturbance observer, what I'm going to get is something like this. It's called like this. So this is with DOD. This is without original. So what we can do is, this is the amount of extra attenuation we can get. Okay, we can get by using this idea. So if your disturbance active in this time frequency range, this really will do a very good job to minimize its effect. Okay, so depending on the disturbance D, if you have a D J omega, okay, so depending on the spectra, okay, spectra. So usually in practice, this is called a narrow band signal. The energy is constrained, is dominant inside certain range. Then this kind of DOB is very effective. Okay, very effective. But I want to give you a warning. Okay. So in control, the art of control is just a trade-off. So in other words, what you gain when you gain something, these are the benefits that we gain. Okay, we gain. At what price? Okay, at what price? Okay, so the price is, because here this is our price to pay, but you spread over to a very low, high frequency here, a little bit higher. So so what I'm trying to say is, but if your noise energy is here and you got amplification here, so as if you didn't do anything worse, so which is good. So there is a very interesting formula. It's called body integral formula. Okay, it says that the integration of Sj omega here and d omega here. So you do a minus infinity to plus infinity. This one will be 0. Okay. In other words, so this is a minus, this is a plus. Is attenuation and amplification. These errors add together should be 0. Okay, should be 0. So in other words, it's just like a water bed. Okay. just a little bit. You get something down, then you get something up. Okay. So what I'm drawing here is exactly the waterbed principle in action. So then the green part here, green part in here, and the red part in here. This is a gain, so this is loss. So gain and loss, they are the same. The only difference is my problem disturbance is in this range. So therefore, this DOB is working, which is practically the case for almost all mechatronic systems. Okay, so let's come back and see IMP. We did, DOB we did. Okay, and we spent about 30 minutes. Okay, so do you like this type of writing? To illustrate, you have to focus. I'll send you this whiteboard copy for you, okay? And also you can refer to what I said. We learned body integral formula. We talked about waterbed effect. We talked about out of control is trade-off. So let me see if anybody's talking to me. I don't see this. Where is the chat box? I don't see my chat box. Auto Edge. I'm in trouble. I don't see your chat box. You send me a message. Okay. What you guys, if you can screen shift them to larger, then would be cool. Okay. Okay. So I'll put this all the feedback in real time. Yes. Oh, it blocks me again. Okay, that's why. Okay. So if you feel this is good, I can continue to explain, but maybe more effective if I use slides right now. I'm going to use slides to show you that the delay compensation issue. So let me give you a myth. Okay, so this is let me give you a very interesting myth. Okay, so this is a very interesting myth. Okay, so when I was a student, I was tricked by my professor on this thing. Okay, so number 3. Okay, number three. Okay, it's called Smith Predictor control. So you know that let me do this. So you say you have a G. Oh no, this is not good. So let's do this. So say for example you have a G of S. Okay, it's your plant. Then you have a delay in here. Okay, you have delay in here. Remember we learned something called K versus tau S plus 1. E minus LS is the first order plus delay time. Okay. So this one represents a very good approximation of a heat or temperature control. Okay. While temperature control are 80% of all control tasks. Okay. So 80% of all control tasks are for temperature control. So learning how to deal with this is interesting. It's very important. But if I put it here, I got a Y in here, I put a controller in here. I want you to see that So this is reference, this is feedback. So I want to see that, what is the T? T is actually, it's a C and G and E and minus LS. So what is here? It's 1 plus C and G and E and LS, okay? So in other words, if the L will influence the closed loop stability, which is reasonable if you have too much delay. Yeah, say for example, you delay a year. So no, I'm joking. But if the L is too large, the system will become less stable. Okay, usually if L goes up, then your stability margin will go down. Okay, or go down. Okay, there's a reason for that. So now I'm going to show you the magic. Okay, with this Smith predictor idea. Okay, this idea will be able to make your T of S is CG1 plus CG and E minus S. So compare this one to this, as if we suddenly made this term disappear magically, okay? So this term disappears, just simply threw away. You know, this is magic, right? So it's magic. Now it's time for me to show you this, how this is doable. Okay, from here to here, your system stability will no longer be affected by this term. This term disappears. How this is possible? Okay, so you should learn because in industry, Smith predictor is introduced to deal with this delay issue. Okay, so that's why we're going to do it for you here. Can you see the slides of the PowerPoint? So this PowerPoint is basically saying that the system, you have different delay in here, the tau d in here. The bigger the delay, the bigger this phase. This is a phase, this is a magnitude. So this is open loop first order plus delay time. Okay, plus delay time. So this crossover frequency will be different. Okay, will be different. Therefore, the ultimate gain decreases. Okay, decreases. Okay. So I need to go back a little bit to see a person's picture. So this person is Smith, O.J. Smith. Okay, so O.J. Smith. And the delay is everywhere. Say for example, you have hot water and you come back, so you have cooler. So the travel length is relatively proportional to the delay. So okay, so there are many cases. Okay, so how to deal with the delay, because the delay will make your phase lost. Okay, margin lost. So you have to detune the PID control, meaning your K should go down a little bit. Or you have to use this model predictive control. Okay. Here we are doing a model predictive control. It's called Smith prediction control. Okay, prediction control. So let's go here. So this is your process. This is a nominal plant. This is a delay part. So we assume this everything with tiered. Everything with tiered is estimation. Ideally, G tiered is G. Ideally, tau delay tiered is tau. That makes sense, okay? Makes sense. Then this is your controller mechanism in this box. So, okay, so what you do is you have a signal called M in here, okay? So this is just estimation. best estimate. This is also best estimate. Okay. So in here, the y tiered can be written as a g tiered. Okay, in here, and 1 minus this one times m of s. So this is estimated one. So then we put together what's the transfer function? It's m divided by epsilon. So this is my controller. So this is my controller CFS. Okay, with this Smith predictor as this. Okay. Once we put this one here and start to, so this is my CFS. The whole thing is CFS. Okay. So put together, we are going to get this overall control function like that. Then we further derive. Okay, further derive. Okay. Well, let's assume this is ideal, perfectly estimated. So this is ideal. Okay. So then this is my controller, Smith predictor controller. Then put everything here. It's very complicated, but magic will happen. This one, magic will happen. Listen. So this G is original plant, and this E originally with this guy it disappears. Okay, disappears. This E minus tau S in denominator disappears. Okay, disappears. So by writing this way, we can simply say, hey, we simply say do this loop. So this is this loop, and then this is separated in here. So that's the magic of Smith predictor. Let us go back to see why this is called predictor. Okay. So if this is y, what is the value here? Okay, so this is y, this is yt, right? What is this one? It's t plus tau d. Is that right? So this signal delayed tau d, then you minus tau d, you are going to get this one, right? So I would like to say, because of this delay, if I know this one is a current one, what is this one? This is the future one. Okay, this is the future relative to the current. Okay. So that's the future. So in other words, if you have this signal times G, M times G, M signal times G will get you a future signal, which is this one. This is my future. So you can see M times G. So there's a, so we should write this one. M times G tiered minus M times G tiered E tau ds. So this is like my real yt, okay? This is like my future t plus td. So the reason we call this is predictive control is exactly because of this term. We are predicting the future, okay? Predicting the future. As if, okay? As if, okay? So that's why this is called predictive control, okay? We are using the future information, okay? And the current information, the difference, to form as a y, okay? As y. So that's why we say a predictive control. So the closed loop signal, you can simply write like this one. So take this W as this one. So delay. But in reality, can you really get the signal? No, it's not possible. They are combined together. How you can just pick into? No, it's not possible. You cannot do it. So just help you to understand it, okay? So if the model is exact, so the delay can be totally removed and out of the loop. So you can achieve much tighter control. The stability is not affected by the delay. So these are all benefits, okay? But in other words, sometimes you have a mismatch, okay? Mismatch. Do you have this model mismatch? Then the compensation is not complete. Then this will cause some additional trouble. But that trouble is relatively small, okay? You have small trouble, okay? So, but you need to double check how big is the trouble, okay? So it's still, sometimes people publish papers on Smith's predictor modifications, okay? So let's see an example, okay? So you have a GFS, this is your GFS, okay? It's delay-free case. So we are trying to see a PI control without delay compensation. So you are going to see that the PI control, then you have a oscillation. You have oscillation, okay? So which is, say for example, I have the system gain, the KC, this is nominal. But if I increase, so this is, so if I increase the KC in here, the system will change, okay? So there's a mismatch. But this is with delay compensator. You can see, compare this 1 and 2, everything is the same. It's still working very nicely. But so, in other words, it's getting more robust, okay? Robust. And the performance is also much better, okay? It's smaller overshoot, okay? So you have a first-hand experience that with and without that Smith predictor, the performance is different. So you definitely deserve to apply in practice, okay? So this is called Smith predictor, okay? Smith predictor, to interpret in a real system point of view, okay? So this is try to help you to further understand. Well, I already explained to you why it is called prediction, okay? So with that, we go back to here about our roadmap for today. So today we try to do internal model principle, disturbance observer, and Smith predictor, okay? And our timing is great. I'm going to next to show you this, okay? So it's a simple exposure to these two topics, okay? These two topics. At least psychologically speaking, they will make you feel confident that, hey, these things were covered in my class, although briefly, but if needed, I can pick them up, okay? So you learn how to learn, right? So that's what I want to comment. So I'm going to do LABView about 10 minutes. So in fact, I have 40 slides in here. I'll go very fast, okay? So it's called a virtual instrument, a virtual instrumentation. So when you have a data, you sample, you visualize it. I want this one look like an instrument, okay? So then you need this virtual instrument platform. So LABView is very popular in industry setting, okay? So understand what are the components within the virtual instrument. So I think we covered this one in another form, but now it is in the LABView term, creating applications. So let me show you, okay? So this is kind of like a virtual instrument. So inside the virtual instrument, so these are the temperature. You double click this one, you will show what's that. So it's called a front panel. So this is just like a front panel. Think about it, you use an oscilloscope, okay? There's the interface between you and the instrument. So it's called front panel. Inside the box, behind the panel, inside the box, okay? So in the front panel, what you can do is to see the signal out, trying to show you, or you can have some buttons you can on and off. You can turn, that's called indicators. You can also do inputs. In this case, this is a mode switch. So you can switch. This is a mode switch. You can switch this one up and down with Celsius or Fahrenheit. Okay, and these are displayed in graphical form and numeric form. Okay, so that's from the panel, and you also have block diagram. So block diagram. For block diagram, this connected to the front panel, and those all the components behind the panel are wired together like this. So here you have a channel, okay? You have a board, it's a DAC board, ADDA board, ADDA board. That board is you insert within a slot in the motherboard previously, but today you can have a USB. You can have the board connected to the computer, not through the slot, but through a USB, okay? So you can see this is also called DAC system, data acquisition system, okay? So if you Google USB data acquisition system, there are plenty. They do not use the slot on the board anymore. But the concept is from there all the times. So here you have the channel, different channels, okay? Channel 3, you have voltage coming in. It's called voltage reading. Voltage reading is basically you have AD, analog to digital, okay? Then come over here is already digital. You times 100. So you have a mode switch here, convert to C or convert to Fahrenheit. So then this is a converter. Then this is the temperature, okay? So that's usually the simplest temperature visualization. So the basic components is signal acquisition is in this box, signal acquisition in this box, okay? Then you have signal manipulation, which is this box, okay? All right, and pull out that one, this is your front panel, okay? There's a panel, directly interface with the user. And from the panel, you can also send the control back to this block diagram, true or false in here. Okay, this temperature control using this as a. So they did a lot of this kind of libraries. Okay, libraries. So it's just like a Simulink blocks. Very similar. So this is called visual block diagram programming. Okay, this programming reminds you what? Lego, right? And they also can, the front panel, they have many other components. You can do stop, pause, indicator, panel toolbar. You can put different types. Also, you have an oscilloscope, waveform graph, okay? Put there, okay? They have different names, and zoom in and zoom out. So this block diagram can be encapsulated, okay? Encapsulated. You can also put a loop signal in there, okay? So you can stop it. So that is called stop the loop. Otherwise, you will continuously real-time sample the data showing you, okay? So this is acquisition temperature block diagram and control the function palettes. So these palettes to me is just like simulating block libraries you can choose from. Then you construct your different operations. So you have graphics, have different icons. There's a tool palettes, different tools like reposition, label, wiring, scroll, and breakpoint, and probes, you name it. Okay, as if you are doing a breadboard circuit. Okay, and they also have status bars. This is too much detail. I'm going to just flash you. So how to create a VI? VI is called a virtual instrument. Okay. Oh, I think I forgot to tell you what is LABView. Lab is, lab. View is actually something different. It's called virtual instrument environment workbench. Maybe. Let me go back. We already have it here. Oh. Really? I think I have a definition of what is LabView. I think you can Google what's that. We are already here. I think probably it's a workshop or workspace. Wiring tips, you don't need to. You can figure out. Like Simulink, you have to work with it. But the basic idea is important. These are very good tools for you to construct an instrument without building a physical instrument. You just build a virtual instrument. And you can do sub-VIs, meaning you can encapsulate some of the functionality into, just think about it like subroutine or function calls. Okay? The benefit is easier to debug, it's modular, you can make the code reusable, maybe you can save memory. Icons, connectors, so sub-VIs. So it's possible you just put this as sub-VIs. So those with common function, and so that is data acquisition. You have sensors, you have terminal blocks, you have cables, you do a dashboard, data acquisition device. This is the slot you put in the computer inside, you plug in a slot. But today, this is done. This is done. It can be USB. Okay, USB, and put this DAC device into a box. Okay, in the box. So with this DAC device, everything here, plus your laptop or desktop, you can put together an overall as an instrument. Okay, and with virtual instrument. So then building an instrument becomes very flexible and reprogrammable, okay, and saving a lot of time and cost. Data acquisition. For data acquisition, I think you probably know this resolution, range, and gain. Loops and charts, these are programming parts, okay, you can do it. Then the waveform, you can, like oscilloscope, you can change it. control graph waveform chart. Just use this box. There are multiple ways to visualize it. They give you all of these things. You don't have to reinvent the wheel. File IO, it's possible you can save into a spreadsheet. So I'm not going to, measuring, monitoring temperature. So we just, so this is the power supply source. This is the terminal board. So, and with the stuff linked to the computer. So this is breadboard for signal conditioning. Okay. So you get the signal in, and where is the board? The board is plugged into the computer, probably underneath the table. So then we just do LABView based for photobioreactor. So everything is put into, this is the panel, okay? So they call it VI panel, okay? So these are the things you put together. In your industry setting, you most likely will be in a system like this. You will be asked to put a monitor and lump all the signal and visualize them, okay? So then you can use different types of visualization. Either, this is called a gauge your temperature in this different ways to show. And this is called do some operation. Okay, different signal you add together. So I suggest that's probably enough for you to get started. You have a basic idea of what's VI. Okay, what's VI. So we should have some of the LABViews, very old versions in our School of Engineering, but we are never integrated into our lab. Okay, we don't have enough time, as you can see. So what I'm trying to do next is to show you PLC. Anybody heard about this term? It's called ladder logic. Ladder logic. You have ladder, then you have logic. So I'm going to stop with this ladder logic, and but to do that, let's first go through what we call it discrete event control, especially sequential control, sequence control. In industry, we have many of such kind of things. Say, for example, you have a production line, you do things, you have a workflow, you do step one, how much time, after that time, you have timer, then you will turn on the next step. So, or you have some button is pressed, then you respond that, okay? So it's called sequence startup or shutdown, okay? So for these sequential processes, step by step, logically, okay, logically. But there are also some conditions add together, then something else will happen. Or you have some interlock logic. That kind of combination should never happen. You can cause explosion, okay? So logically, I want to interlock them, so it will never happen. So how do you ensure that? So sequential control is exactly solving that kind of control. So everything you did is called continuous or digital control. This is called event control. You see some event, you respond that. How we did that is called using the control relays and PLCs, okay? Or directly using computers, you have logic in there. I'm going to mainly show you this one. And in the end, I'm going to show you the PLCs, okay? So to understand, our starting point is to say something called electromagnetic relays. So when you have a coil, okay, with voltage on, okay, you have a voltage on, then you have a magnetic field produced. Then you will turn another thing called on or off. So let me give you an example. So this is called contact. Okay, so you have a contact. So that means those are called switches. The coil energized will activate a set of switches, is on or off. So this is a mechanical relay that you have a coil. Once you add voltage on the coil, this switch will put from off to on or on to off. Okay, so it's just like you have a switch in here. So if you have a magnetic field, you will suck into here, right? Or you have a magnetic in here, they will suck into here. Okay, so that's the point. So NC means normally closed, normally open. So for the normally closed, the switches here is 1, 9, okay, 1 to 9, okay, 1 to 9 as normally closed. 2 to 10 is normally closed. 3 to 11 normally closed, But without electricity going to the coil. If you have the electricity going through the coil, you will energize the magnetic field so that it will attract the contact point to here, to here, to here, to here. So in this case, I call 5 to 9 pair. 5 to 9 pair is normally open. Okay, normally open. 6 to 10 is normally open. This is normally open. So understand that, you will be able to see some other symbols. It's called a control relay. Control relay. So when you don't have a bar in here, it's called normally closed. This is normally open. So then there is a control coil. So this is CR. So this is the number, the CR is a control relay 1's coil. So we actually call a control coil. If coil has electricity, this will be on, this will be off, okay? We will change the state, So that's by energizing here, okay? The turn on that coil circuit. There's another thing called time relay. So meaning you have time, after a certain time, there will be from NC to open, from NO to close, okay? And also I have a lights, okay, red lights, green lights. So and also some buttons. Buttons usually is by human, okay? Or limit switch. So you travel, you hit it from here, then it will be closed. But from here, if you hit it this way, you will make it open. Okay. So this is called mechanic limit switch. So this is symbol LS. PB is just push button. Pressure limit also. Okay, pressure limit. Temperature limit. So this is the symbol. If the temperature is going too high, you hit the limit, the switch will off. So I think you have some ideas in daily life. If you overheat something, then the circuit will be automatically turned off. But when you cool down, you can still use it. Okay, so that's because of this thing. Okay, temperature limit switch. It's a kind of mechanical relay. Okay, mechanical relay. Okay. And also you have a motor here. The symbol of motor is like this. I think the motor is here. Yes, we have motor here. So depending on the current direction, it's a forward or reverse running. Okay. So these are very basic ones. Now, now I'm going to finish in 4 minutes. So relay logic, or relay ladder, okay, or ladder logic, okay, ladder logic. So basically, you have two rails, okay. This is a two rail, okay. This is the rail, okay. So this rail has voltage. This rail is ground, okay, ground. So if you press the button, this one or this one, or this one or this one, it will make the motor stop. Stop. Okay, stop. So this is called forward relay. So now it's forward. So you push the button here. Okay, then this is closed. So then this forward relay coil. This is the coil, control coil, called FR. So FR here, this will be connected. Okay, this will be connected. Okay. If you push this one is off. Okay, and remember, then this one FR is also connected, and this one is already connected. So then this one will turn. We'll have current to do this way. Okay, and this one is disconnected. It's for the running. Okay, for the relay. So then this kind of like a kind of interlock. Okay, this kind of interlock. If I have electricity, you don't have. Okay, so these are the logic things that are kind of interesting. But this kind of thing is called ladder logic. Okay, ladder logic. This is ladder logic. We don't have time to go through all the combinations of logic, but fortunately today we don't have to manually do this type of mechanical relay logic. We can do programmable logic using a computer. Inside the program logic is similar to a computer. Okay, so you have CPUs, you have memory, you have timers and stuff like that. So hardware software interface. So then so using a PLC you buy is like you buy a brick. Okay, it's like a brick. So it's like a small computer. Right? You can be very efficient, save time, and cost is low. And rewiring, you don't have to do it. You just do it in the software. And programmable logic. So this is a program. So this is in the coding. They have an interface of programming. So you simply, again, it's visual programming like it's Simulink. You can do this type of programming in a computer GUI. Okay, to do that. Then you can also simulate it to see whether the logic is right, everything is right. They provide a lot of different functions in the different PLC systems. You have logical operations, you have arithmetic operations, okay, and data in and out, and so on and so forth. And also like looping, jumping, and condition, programming controls. So there are some examples. Probably I don't have time. So if you have something go on, then you count up, then you should turn on this. Then the alarm will sound. Okay. Okay. So yeah, I think there are several examples. Then, but You can see it's a very early book, 20 years ago. Programmable logic controllers. So I hope everybody today, let me see, I have 17 students. That means 23 of them didn't come. I don't understand. Because of their time management, they probably willing to watch it without attending it. I don't want to say the time management is bad or you are not self-disciplined. I don't want to say that, but it's better as a student, you discipline yourself that way. When it's class time, just do the class, okay? I know it's difficult, but anyway. So anything I talked about today could be in the final exam. Just give you a warning, spread the word, okay? You cannot say in the end, say, oh, I'll put something in there, you never explained to me. No, I explained, okay? Anything I put in the final exam, I covered in the classroom for sure, okay? Let me see if you have any final questions you want me to tell you. Can you see shipment for what is final exam? It's in syllabus. Okay. Let me actually I have a syllabus opening here. So final exam is actually according to our definition here is May 13, 8 a.m. Wednesday. Okay. I'll send out reminding. Okay. I'll send out more than one reminder. Okay. So you don't have an excuse. Oops, I forgot. You know. I'll give you. So we don't need computer to compute. We don't need MATLAB. We don't need a calculator as well. So it should be just a pen and paper should work. Okay. When I say sketch, you should sketch. Don't use the computer. No. I'll answer more questions like that Friday class time, and I suggest everybody should not miss that. So, any other? Let me see. Do you have any other questions? Okay, what's that? So, Karen, no. About it, how long? It is said in here. It's said in here 3 hours, 8 to 11. Okay. This is all preset. So, all right. Any other things? Let me see. It's 3 hours. Okay, 3 hours. I can answer more questions like that on Friday. Okay. Yes. I have more information. I can even tell you what kind of what structure it should look like. You should expect. You'll have no surprise if you learned. I can tell if you have learned. Okay. So I can even tell, are you in A level or B level or C level or D level? I can tell. It's pretty consistent. I'm always generous to students, so I keep a wide list. So if you visited my office hour, if you attended office hour, I'll write down your name, so, as I promised. So I have to finish here. Okay, we'll talk to you later. Okay, bye-bye.